This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. We could easily perform the same analysis for a range of load resistance values from 0, representing short circuit conditions, up to infinite ohms, representing open circuit conditions, but this would take all day and then some. It's for this reason we use spreadsheet software to visualize the implications of maximum power transfer theorem. For the purposes of this analysis, we'll assume open circuit conditions, i.e. infinite resistance, is approximated at extremely high resistance, let's say 10 kiloohms. If we're to plot voltage across and current through the load resistor as a function of load resistance from 0 to 10 kiloohms, we obtain the following graphs. These results should be pretty self-explanatory. At short circuit conditions, i.e. when the variable load resistor R load is adjusted to 0 ohms, the voltage drop across it is 0 volts and rapidly increases as R load increases. At approximated open circuit conditions, when R load is extremely large, voltage approaches the maximum drop of 18.2 volts. A plot of current in blue is just the opposite. At short circuit conditions, i.e. when the variable load resistor R load is adjusted to 0 ohms, current is at a maximum of roughly 68 milliamperes and precipitously decreases as R load increases. In approximated open circuit conditions at the far right of the graph, when R load is extremely large, much less current flows. In summary, as the load increases, voltage starts low and goes high, and current starts high and goes low. Power, however, is the product of voltage and current. In short circuit conditions, the far left, high current flows through the load resistor, yet it experiences no voltage drop. In short circuit conditions, power dissipated by the 0 ohm load resistor would be 0 watts. In approximated open circuit conditions, the far right, voltage drop across the load resistor is high, yet no current would flow through it. In true open circuit conditions, power dissipated by the load resistor would be 0 watts. In between these two 0 watt regions is where the magic happens. Traveling left to right from short circuit conditions to approximated open circuit conditions, voltage increases and current decreases. Along the way, voltage and current form a maximum power product that peaks when R load equals the Thevenin equivalent resistance and quickly subsides. If we were to zoom in on the regions surrounding peak power, you'll notice regions in the low side shoulder of the power peak experience more current draw but less voltage drop. Regions in the high side shoulder of the power peak experience more voltage drop but less current draw. The maximum power point is a compromised condition in which two interrelated voltage and current values form a maximum power product. Note that the power curve peaks out at roughly 310.5 milliwatts in the region of 267.1 ohms as expected. Load resistances on either side will experience less than maximum power. Regions where R load is on either side of the peak, like our two representative examples at half the Thevenin's equivalent resistance and twice the Thevenin's equivalent resistance, would be in the shoulder regions of the peak power curve. The maximum power transfer theorem really is that simple. A variable load resistor will receive maximum power from a circuit when its resistance is exactly equal to the Thevenin's equivalent resistance for that circuit. The only tricky parts are 1. Obtaining the correct Thevenin's equivalent circuit, and 2. Using it correctly. Note the load resistor is but one of two resistors in the equivalent circuit, the other being RTH. Again, at maximum power conditions, our load drops half the Thevenin's equivalent voltage. The other half of ETH is dropped across RTH, which also experiences the same current given that Thevenin's equivalent is a pure series circuit. This is to suggest that at maximum power conditions, RTH dissipates just as much power as our load, which leads us right into a discussion on efficiency. It needn't be surprising that maximum power conditions are not efficient conditions. One would not consider using a dragster to perform the daily commute, nor one would consider entering a Prius in a tractor pull. Not only would you lose, you'd look like a total nerd doing so. Maximum power conditions are inefficient, as efficient conditions are less than powerful. At maximum power conditions, an application of the power equation demonstrates the source delivers 620.9 milliwatts of power to this system, of which only 310.5 milliwatts is put to beneficial use by the load resistor. The remaining 310.5 milliwatts of power dissipated by the Thevenin's equivalent resistor would be considered a loss to this system. Efficiency is the ratio of usable power output over input. Of the 620.9 milliwatts delivered to the system by the source, only 50% is put to beneficial use by the load resistor. At conditions other than maximum power, efficiency changes. Consider a case when our load is twice the Thevenin's equivalent resistance, or 534.3 ohms. During these conditions, V load equals 12.1 volts, I load equals 22.7 milliamperes, and power dissipated by the load equals 276 milliwatts. The source, however, delivers a total of 414 milliwatts to this system, of which 276 milliwatts, or roughly 66.7%, are being put to good use. Any power dissipated by RTH is considered a loss to this system. In this case, power delivered to the variable load resistor is less than maximum power conditions. However, it's being used more efficiently. If one was to plot a graph of efficiency as a function of load resistance, one would find that at maximum power conditions, when our load equals RTH, efficiency is a paltry 50%, however, increases as resistance increases. At conditions other than maximum power, power delivery is less than maximum, but depending upon which side of the maximum power condition you're on, efficiency can be more or less than 50%. In summary, a load resistor will experience maximum power when its resistance is equal to that of the Thevenin's equivalent resistance for the circuit under inspection. At maximum power conditions, the load resistor will always experience a voltage drop of half the Thevenin's equivalent voltage, and the circuit will operate at 50% efficiency. Load resistances less than maximum power conditions will experience more current but less voltage, and as a result, dissipate less power. Similarly, load resistance greater than maximum power conditions will experience more voltage but less current, and as a result, dissipate less power. Alright, this concludes the theoretical portion of this lecture. Is that it? No, your exposure to the maximum power transfer theorem is far from over. Really, the only way to understand maximum power transfer theorem is by doing the maximum power transfer theorem. In this spirit, stay tuned because I've got another complete lecture coming your way real soon featuring nothing but applications of Thevenin's theorem and the maximum power transfer theorem. Believe me, you'll get plenty of practice. In conclusion, we learned a variable load resistor will experience maximum power from a circuit when its resistance is exactly equal to the Thevenin's equivalent resistance for that circuit. Additionally, we discussed efficiency and took a look at voltage, current, power, and efficiency curves for varying load resistances. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.